In this lecture, we're going to continue our discussion of isomers, but move away from the constitutional isomers and into conformational isomers. And so as we look at this, let's remind ourselves of what constitutional isomers are. And maybe we even start with just isomers. So isomers are molecules. I think I have purple for that. We have the plural molecules, not just a single molecule. A single molecule is not an isomer. It's an isomer of something else. So it's always a comparison of multiple molecules. But these are molecules with the same elemental composition. They have the same elements. The same elemental composition, but different 3D arrangements of their atoms, because it's plural. So we're comparing two molecules at least, maybe more, that have the same elemental composition, for example, C5H12. I won't get over that one. Anyway, so we have the same elemental composition, the same number of carbons, hydrogens, oxygens, whatever it is, but they're just arranged differently. And so we looked at an example where the atoms differed in connectivity, and we call that constitutional isomers, or that class of isomers, constitutional isomers. So a class of isomers where the structures differ based on differ in connectivity. Or bonding. Okay, so we had looked at these two definitions before. So far, this is just review of sorts, right? But I said we were going to get into a new type of isomerism or class of isomers called conformational isomers. So I'm going to truncate the definition to, I'm not going to use the words same elemental composition over and over again. Instead, I'm just going to say these are isomers. So when I say isomers, I mean at least a pair of molecules with the same elemental composition. Isomers where the structure differs due to free rotation over sigma bonds. So free rotation over sigma bonds. And these are usually, but not always, just usually, CC bonds. But they're always sigma bonds, never pi bonds, because pi bonds don't undergo free rotation. Okay, so when molecules undergo free rotation, their structures change. Their elemental composition has not changed. Their structures change. Now the bonding and connectivity has not changed. So they're not constitutional isomers. It's just their arrangement in three-dimensional space is now different because of free rotation over sigma bonds. So let's look at an example. So we've got this molecule versus this molecule. If you compare both of their structures, they each have 6 carbon atoms. There's no double bonds or triple bonds or halogen atoms, so we assume that they just are fully loaded or fully saturated with hydrogens. It's going to be C6H14. So they both have the same composition of elements, but their structures are in fact different. Okay, if you look, the structures are different due to free rotation over the bond in my numbering from 3 to 4. Just by spinning that bond around or rotating that bond, due to the fact that it's a sigma bond, we get to conformational isomers. Conformational isomers each have the same name. Both of these molecules are indeed the parent structure hexane. So we can't distinguish constitutional isomers by IUPAC naming, which is something that was useful for distinguishing constitutional isomers versus things that just have rolled around, or as we're seeing now, undergone free rotation in space. So conformational isomers, let's capture that again. Conformational isomers are different structures. Let's make sure that we remember that. If they're not different structures, they're not isomers of each other. Are different structures. Okay? And where they are different is free rotation over sigma bonds, or single bonds. All single bonds are sigma bonds, remember? So they are different structures, but they do not have different names. Sometimes we add qualifiers to them, and we'll look at that at the end of the module in something called Syn, Anti, and Gauche. Don't worry about those words now. But sometimes we add qualifiers to designate or characterize each of the conformations, but in terms of IUPAC names, they do not have different IUPAC names. Okay? And conformational isomers, they are important to study for multiple reasons, not least of which is it helpful for you, because if you understand conformational isomers, you can understand why two molecules are not constitutional isomers, like we saw in the previous page of notes. We had those two hexane structures, and if you understood conformational isomers, you could see why those two wouldn't be constitutional isomers, which differ in the connection points of atoms. So the other reason why conformational isomers, let's just speak more broadly beyond this class, why they're important, are conformational isomers provide or maybe influence a molecule's properties. We've talked a lot about what we would call small molecules, and that's very useful to start with. But if you want to look at some larger macromolecules like DNA, proteins, these are biomolecules, plastics, these sorts of things. All of these adopt unique conformations. Which greatly influence their properties. I think it's really interesting to study molecules in the molecular space. I have a passion about it, I'd say. Okay, whatever. It's interesting and fascinating. But for the vast majority of people, it's understandable that they're not that interested in looking at like the fact that a sigma bond can rotate. They're more interested in the bulk properties. That is, chemists supply chemicals for the greater good of society, we hope. A lot of the properties of these chemicals, which is the things people care about, they care about what these properties are, whether they're physical or chemical properties. A lot of these properties are governed based on what sort of conformational isomers are available to the various molecules, whether they're small, tiny molecules, which I guess less so important, or the really big molecules, like plastics, for example. Their properties can be influenced by their ability to undergo free rotation in the bulk state or when they're processed. Proteins, their entire function really is governed by the conformational space, or the number of accessible conformations that a protein can exist in. And DNA packages and bundles itself up by adopting unique conformations, allowing us to fit somewhere on the order of magnitude of 6 feet of DNA within every single cell in our bodies. I believe that's correct. I remember my introductory biology well enough, I think. Okay, so in terms of proteins that, we can kind of keep talking about this for a second, proteins that adopt the wrong conformational isomer are said to be misfolded. That's a technical term. Misfolded. And these proteins won't work. Not only will these proteins not work, and if they don't work, the body usually, or the cell usually finds a way to digest and decompose these proteins so they can use the building blocks over again in a recycling process. But if they can't, these can lead to diseases, which are called prion-based diseases. And a classic example of that would be mad cow's disease. So that's just kind of a brief look into the world of conformational isomers, and hopefully a discussion of why they're important. What we'll do next is look at effective ways of visualizing and thinking about conformational isomers on a 2D piece of paper, a topic called Newman projections.